তুলে দেখো আর এই যে এখন দেখতে পাচ্ছে ওখানে ঢুকতে পারবো লাইভ করা আছে ইস লাইভ ওকে আর হচ্ছে
আচ্ছা অ্যাডমিট করে দেবো কি এমনি আর তো 20 মিনিটের কম আছে আপনাকে অ্যাডজাস্ট করতে আচ্ছা অ্যাডমিট করে দেবো কেন
আমাদের কারণ ইউটিউব লাইভ অবশ্যই দেখাচ্ছে বা আমার নেট আমি কি বলছি আপনি ভাবুন বলছি যে দেখুন টাইমটা কতটা ডিফারেন্স বেশি ডিফারেন্স নেই মানে আছে ওই কয়েক সেকেন্ড আচ্ছা এরা ওরা শুনতে পাবে এরকমই দেবো আচ্ছা এটা স্লো ভিডিওটা এখন ভিডিওটা পুরো না আরো পরে আর 16 মিনিট আছে আচ্ছা পরে করবেন না দেরি হয়ে যাচ্ছে আর 16 মিনিট আছে লাইভ একটু স্লো হয়ে গেল কেন বুঝতে পারলা not receiving any চার্জিং এ কোনটা ওইখানে কোন মিনিটে যখন শুরু করবে রেকর্ডিং অপশনটা চালু করে দেবে কারণ তাহলে পুরো প্রোগ্রামটা আমাদের রেকর্ড হয়ে যাবে ওই আমাদের ড্রাইভটা আজকে কিন্তু নেটটা স্লো কাল বিরাট ভিডিও ছিল আজকে ইউটিউব ইজ নট রিসিভিং এনাফ ভিডিও এইটাকে বন্ধ করে আবার আবার দেবো জানান না একদিন না না করবেন না কারণ কি না স্ট্রিমটা বন্ধ করতে যেটা হবে আমরা যদি স্ট্রিমটা বন্ধ হয়ে যায় তাহলে তো আলটিমেটলি এই লাইভটা শেষ হয়ে যাবে এর আগে দিনে মনে আছে তো কারণ এখন এখন স্টার্ট করে দিয়েছেন যখন লাইভ যখন শুরু হয়ে গেছে সুতরাং আমার মনে হচ্ছে এরপর যদি বন্ধ করে দিই তাহলে আবার নতুন লিঙ্ক দিতে হবে না না লিঙ্ক ওই লিঙ্কটাই চলবে আমার মনে হচ্ছে কন্টিনিউ হবে না কি করে হবে আমি দেখলাম তো চেক করে দেখেন 4টায় আমার টাইম হলো শিডিউল করা আছে তো শিডিউলটা চালাবো তো কিন্তু আপনি তো আগে স্টার্ট করে দিয়েছেন শিডিউল টাইম হলেও তো ওরা শুরু করে দিয়েছে আমরা দেখুন এখানে আর দেখাচ্ছে না এদিকে লাইভ লেখা আছে আর কিন্তু ওই টাইমারটা দেখাচ্ছে না কারণ আমি যেহেতু আগে
কিন্তু আগের দিন আমাদের 4 ঘন্টা করে স্টার্ট
দিয়েছিল আমি মেন আর
যদি আগে স্টার্ট করে
আগে স্টার্ট করে দিয়েছিস সেই অনুযায়ী কি আছে তবে হয়তো সময় আছে যেমন হচ্ছে তুমি যদি কি করিস টাইম দিস 15 মিনিটের আগের বেশি শুরু করতে পারবি না আমি যে কালকে ডেট দিয়েছিস আমি বলি না আজকে শুরু করবি পারবি 15 মিনিট আগে স্টার্ট সেরকম হয়তো কিছু একটা আছে এখন এগুলো পর এটাকে লাইনটা কেটে দিলে একবার ভালো হতো
আচ্ছা লাইন কাটা যাবে
আমার মনে হচ্ছে যদি আবার কেটে গেলে আবার লিঙ্ক তৈরি করে সবাইকে জানানো মুশকিল
আর সম্ভব স্যার এন্ট্রি শুরু করে দিন
মাউসটা ঠিক করো আচ্ছা এটা কি চার্জার চার্জ হচ্ছে
একটু পরে পরে এটা রাখি
বসো বসো ওখানে এমন হয়ে গেল দেখো এখানটাতে এই লেখাটা ঢুকে গেল এটাকে দাঁড়া এই যে স্ট্রিম সেটিংসটা পুয়ার হয়ে গেল
আমি কি লগ আউট করে অন্য একটা সেশন থেকে লগ ইন করতে হবে আমার ওয়েবক্যামটা একটু ঝামেলা করছে ঠিক আছে গ্রেট ঠিক আছে
আউটসাইড জেগে কলেজ সবাই আউটসাইড জেগে কলেজ পুরুলিয়া
পুরুলিয়া ওখান থেকে বলেছে কানাই যাইছে হ্যাঁ
হ্যাঁ হতে পারে আজকে স্লো হয়ে গেল বুঝলে হ্যাঁ আজকে স্লো দেখাচ্ছে ইউ ইজ নট আর লাইট কাটতে পারছি না তিনটা যদি পাল্টে যায় কালকে বিরাট শুরু করেছে স্টার্ট হয়ে গেলে
total receipt from tax you tax okay around
না না সাউন্ড বন্ধ করে নি। ভলিউমটা কর। এবার কানেকশনটা একটু নেব। নাকি সাউন্ডটা বন্ধ করে বলছে এ রঞ্জন
এটা কি স্যার ওই ভলিউমের মধ্যে সিম্বল দেখা যাচ্ছে ব্যাটারির কাছে ওটা
কোনটা কোনটা
ব্যাটারির কাছে
এটা মাইক্রোফোন এই সেটিং এর কি বন্ধ হচ্ছে হ্যাঁ আমাদের আওয়াজগুলো চলে যাচ্ছে এইটাকে বন্ধ করবো কালকে এটা দেখলে ব্যালেন্স করতাম তো আমি তো
এইখানে ভলিউম অপশন আছে
আমি তো এইটা শেয়ার করেছি তো এর সাউন্ডটা বন্ধ করে দিতে হবে এর সাউন্ডটা বন্ধ করলে হয়ে যাবে কন্ট্রোল দেখি এই অডিও এগুলো বন্ধ হলে পরেরটা যদি না শোনে আবার শোনারও ঝামেলা পড়ে যাবে সেটা আমরা দেখে রাখি চেক করবো কোনো কি সেটা বলছি কেউ বসে বসে বলবে তাহলে সেই সাউন্ডটা আর হচ্ছে দিয়ে এর যদি সাউন্ড কম হয়ে যাবে এটা sound দিয়েছে তো হবে তো হবে কিছু করার নেই
আমাদের তো কিন্তু তাদের যদি তোমার ভালো না হয়
না
নেটওয়ার্ক
আরে আরে বাবা কে দিলে তো নেটটা দিয়ে বরং আমরা একটা কাজ বুঝছো তো
ওখানে করে
ঠিক আছে সেটা যেহেতু স্পষ্ট রয়েছে
ওখানে গিয়ে কথা বললেই তো
কিন্তু এই স্পিকারটা এইটা 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 তাহলে বন্ধ করে না 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 এটা বন্ধ করে না না না
এটা দিয়ে করবেন
আমি বলছি এটা দিয়ে কিচ্ছু করবো না এইটা দিয়ে জিনিসটা হচ্ছে সে এই একটা সফটওয়্যারটা সে ইউটিউব ফেলছে তাহলে এটা তো তার মানে আমাদের সাউন্ডগুলো নিচে রয়েছে
না এটা বন্ধ হয়ে যাচ্ছে সিস্টেমটাই বন্ধ
এই এটা লাগানো হয়েছে
না না এইটা তো বন্ধ আছে
ও আচ্ছা আচ্ছা ও তাহলে হ্যাঁ
এখানে হেডফোন লাগালে কি শুনতে পাওয়া যাবে বাইরের আওয়াজ? তো যদি আমি হেডফোনে
না না কোনো তোমার সাথে কি সম্ভব ভিতরে আওয়াজ এটা প্রোগ্রামিং করা যে ওখান থেকে আওয়াজটা আসে তাহলে
कैसे जाएगी तो लल्ला को कह रही हूँ लल्ला को हम संभाल लेंगे
Nisha Malhotra, please stop your presentation. Nisha Malhotra, please stop your presentation. Please stop your presentation.
না স্যার তো এ করে দিলে একটা দেখাবে আর প্রোডাক্টটা কোন দেয় আর ভাই এখন আগে যে পাবে না ওই খুশি আয় না ওরা প্রোগ্রাম কাটতে স্টার্ট করে দেবে
কিন্তু কেন দিয়ে
এখানেই আছে
আর না প্রিন্সিপাল রেডি হলো কিনা এটা জানি
ওটা তো প্রিন্সিপাল ঢুকে গেছে কারণ জেকেসি
কিন্তু
বলবে
কোনে এটা তো
আসা যাওয়া অ্যাক্সেপ্ট হ্যাঁ ওইটা এটা
এইটা অসুবিধা হবে মাইক্রোফোন আদিগত হবে
এটা কি হয় এখানে কি টাইপ করো হ্যাঁ
এইটা একটা প্রশ্ন বলেই তো আমরা তো
আচ্ছা
চলো চলো এগুলো ওটা খুলেছে তুমি কি এটা থাকবে
আমি
আচ্ছা
edit করবো সময় সব একসাথে
করে না এটা
পুরো digital
চেঞ্জ করতে হবে। হ্যাঁ এটা চেঞ্জ করতে হবে। আপনি কোনো এটা চেঞ্জ করে দেন। হ্যাঁ তো ঢুকবে
হ্যাঁ আর প্রিন্সিপালের পদ তো আপনি আসবেন
হ্যাঁ তো না এটা চেঞ্জ স্টার্ট করে দিন তাহলে
সেটা স্ক্রিনটা স্টার্ট করে দিন।
স্টার্ট করে দিন আপনি করে দিন আমি তো কোনটা সব রেডি আছে দেখো
হ্যাঁ হ্যাঁ হ্যাঁ। হ্যাঁ,
আমি আসি দরকার আছে দেখাচ্ছে দেখাচ্ছে কোনো ওটা তো অ্যাকসেপ্ট করছে এটা তো অ্যাকসেপ্ট করছে হ্যাঁ হ্যাঁ সে ঠিক আছে আমি যাতে সেই দেখা যায় ওই মুখগুলো শুধু দেখাবে তাই তো হ্যাঁ মানে দেখি দেখো
ক্যামেরা
এবারে দেখো না কি দেখাচ্ছে
না দিলেও চলে ক্যামেরা।
এই তো লাইভ স্ট্রিমটা দেখো তো ইউটিউবে না না এটা অন না ওটা ওখানে দেখো এখানে আচ্ছা কি দেখাবে না ইউটিউবটা চেঞ্জ হলো না যে এটা বেরো গেল কেন অ্যাকাউন্টে থেকে বেরোলো তো এটা এই
Good afternoon, everybody. First of all, am I visible and audible?
Yes, sir. Yes, sir.
Okay, thank you. Welcome and good afternoon, everybody. First of all, as the secretary of this first national webinar on mathematical analysis and quantity organized by Department of Mathematics, Jagannath Kishore College, Purulia, West Bengal, I want to take the opportunity to welcome you all mathematics enthusiasts from our country and also outside of it. We are really excited about your responses on this event. Without wasting time, let's get on to the business. Though it is mentioned in the invitation mail, I want to remind you that please turn off your microphone and camera during the sessions. And if you have any questions or queries, please feel free to ask them in the chat box. The link of the feedback form will be given in the chat box at the end of the session, and you are requested to fill this up properly for the smooth preparation of your e-certificates. Now, I want to invite our Honorable Principal, Dr. Shantanu Chattopadhyay, Associate Professor, Department of Physics, to deliver his welcome address. Sir, please.
Thank you. Good afternoon, everybody. Our respected resource person, Dr. Supriya Bhaur and Dr. Somir Kaur, our respected IQC coordinator, Dr. Rosok Agarwal, head of the Department of Mathematics, Dr. Ganesh Chandra Gorai, our senior teacher, Associate Professor, Dr. K.L. Dotto, and other colleagues in our mathematics department, colleagues of our college and from other colleges, and our beloved students, and all participants of this program. On behalf of JK College Purulia, I welcome you all in this one-day national level webinar, Mathematical Analysis and Probability. Actually, first, let us introduce our department to the other participant from other colleges. Actually, mathematics department of our college is a very good, excellent department, and it is a famous department in our college. The performance of this department is continuous and very good. And this year is the completion of 20 years of PG in mathematics in our college. And the topics of this webinar is very interesting. Actually, we are all waiting for this interesting topic, probability. Actually, taking decision for future events, even in all scientific process, probability and distribution function plays a very important role for taking correct decision. At the same time, the properties of function is very much important, not only in mathematics, in all sciences. So I hope all of us will be benefited from this webinar. Again, I'm completing, actually I don't waste any time. Welcoming all, especially to our resource person, Dr. Supriya Bhaur from IIT Kanpur, and Dr. Somir Kaur from IIT Jammu, and all participants of this webinar. Thank you.
Thank you, sir,
Over
for
to-
your nice speech. And now I want to invite our Honorable IQAC Coordinator, Dr. Ashok Agarwal, Associate Professor, Department of English, to deliver his valuable speech on this very event. Sir, please. Agarwal, sir, can you listen?
Yeah.
Oh, thank you, sir.
Very good afternoon, respected Dr. Shantanu Chattopadhyay, Principal, JK College Purulia, respected resource persons today, Dr. Supriya Bhaur, Assistant Professor in Mathematics, IIT Kanpur, and Dr. Somir Kaur, Visiting Assistant Professor in Mathematics, IIT Jammu. Respected and dear colleagues, especially from Department of Mathematics and other departments, all teachers of my college, colleges from the district, colleges outside district, colleges outside West Bengal, and all our beloved students attending this webinar. Warm welcome to one and all in this one-day national webinar on mathematical analysis and probability, being organized today by Department of Mathematics, UG and PG, in collaboration with Internal Quality Assurance Cell, Jagannath Kishore College, Purulia. As the coordinator, IQAC, I express my heartfelt joy in being a part of this webinar on two such important topics. Technically speaking, as our principal already has noted, mathematical analysis is a branch of mathematics dealing with limits and related theories such as differentiation, integration, measure, infinite series, and analytical functions. In other words, it is of great importance for algebraic geometry, number theory, applied mathematics, as well as for physics, hydrodynamics, thermodynamics, and various other branches of engineering. On the other hand, probability is the likelihood or chance of an event occurring. If I may explain it in the language of a common man, I may cite an example. When two captains in a cricket field go for a toss, whether the coin that is flipped will show heads or tails is equal. That is 1 out of 2. This is probability. Thus, we may very well understand that the two topics chosen for discussion today are of great relevance and importance. I sincerely wish this webinar will enrich all of us, and I once again welcome and thank all of you, and especially our two resource persons who have consented to be our speakers today. Thank you very much.
Thank you, sir, for your beautiful lecture about the interaction between analysis and probability. And this is our goal for this seminar, to introduce analysis and probability as a interacting subject. And this is our goal. So now I want to request our Honorable HOD, Dr. Ganesh Chandra Gorai, Associate Professor, Department of Mathematics, to introduce our first speaker, Dr. Supriya Bhor. And yeah, thank you, sir.
একটু শুনতে পাবো তো? আমার সেটিং ফেটিং দরকার না, আমার হচ্ছে হ্যাঁ দরকার। লাইভ স্ট্রিমিং এরকম
Good
হচ্ছে?
afternoon.
ফুল স্ক্রিন?
Welcome everyone to today's webinar on mathematical analysis and
ও
probability.
আচ্ছা আচ্ছা।
In this pandemic situation, webinars or webcasts organized by various institutions are becoming important parts and powerful tools of academic activities to exchange ideas and research activities
একটু
among
হয়ে গেছে।
academic communities. Many institutions already have started such programs with much success. We, the Department of Mathematics, Jkc College, are happy that we are also included in this family through this webinar. We have got a huge response from interesting participants and from every corner of the country and few outside of the country. More than 1,000 participants have been registered for this particular webinar. Due to limitation, we cannot provide them all in Google Meet platform. Many of them are now watching this event through YouTube link. We express our gratitude to our principal sir, Dr. Shantanu Chattopadhyay, whose constant encouragement and support help us to make possible this webinar. We are grateful to our college IQSC coordinator, Dr. Ashok Agarwal, who always inspire every department of our college to organize such academic activities throughout the year. On behalf of our department, I am very hearty gratitude to the speaker, Dr. Supriya Bhor, and to Dr. Somir Kaur for accepting our invitation in sharing their graceful ideas and thoughts in today's webinar. I hope we all enjoy and will be enriched attending this webinar. In this connection, I appreciate the leading supervision of our two younger teachers, Dr. Gopal Datta and Dr. Debabrato Chakraborty, for their constant efforts during last 1 month to make this event successful. I am grateful to all the teachers of our department for their cooperation, involvement, and dedication as a teamwork in the entire process. Before we get started, I shall go over some specific things you will need to pay attention. Please always keep your microphone mute and off your video during webinar. Please don't try to start any presentation during the webinar. Please do not use the chat box to greet each other or give your attendance. You will have the opportunity to submit text questions to today's presenters by typing your questions into the chat box. You may send in your questions at any time during the presentation. We will collect this and address them during the question and answer session at the end of this presentation. In the question and answer session, you may ask questions directly one by one to the presenter after making unmute your speaker. Once you have today's webinar, you will receive a follow-up email within 24 hours with the feedback link of today's webinar, and we would appreciate if you would complete that by providing your valuable feedback. Participants will get each certificate only after filling up the feedback form. I am pleased to introduce now today's first speaker, Dr. Supriya Bhaur, Assistant Professor of Mathematics, IIT Kanpur, who will deliver his talk on a very interesting topic, point losses and divergence of the harmonic series, an interconnection between analysis and probability theory. Dr. Supriya Bhaur is a brilliant young mathematician in the field of stochastics, differential equations in finite and infinite dimensional space. Hilbert valued stochastic process and its applications in various problems. His academic career started as a BSc Mathematics Honours from Ramakrishna Mission Vidya Mandir, Belur, Howrah, under Calcutta University, and he is the university topper. He obtained Master of Mathematics, M.Math, from Indian Statistical Institute and PhD from Indian Statistical Institute, Bangalore Center. Before joining IIT Kanpur as an assistant professor, he was NBAM National Board for Higher Mathematics Scholar and a postdoctoral fellow at TIFR, Tata Institute of Fundamental Research Center for Applicable Mathematics, Bangalore. He has many research publications in his field in various high-index international journals, including SCI indexed and Scopus journals. On behalf of the Department of Mathematics, JK College Purulia, thank you all for joining us for today's webinar and have a great rest of your day. Now I request Dr. Supriya Bhaur to deliver his talk. Dr. Supriya Bhaur, please.
Dr. Gorai, thank you for the introduction. I hope I am audible. Can you please confirm? Dr. Gorai, can you please confirm if I am audible?
Yes, very much.
Okay, thank you. Thank you for the confirmation. All right, so welcome everyone. So let us have a wonderful discussion ahead. I'll be talking, I first wish to thank the organizer for inviting me to deliver a talk at this occasion. And I am very happy to take up the invitation and discuss this interesting topic of interface between probability and mathematical analysis. All right, so I'll start my presentation. Right. I hope this is visible for everyone. So I'll be talking about this point tosses and divergence of harmonic series. And as Professor Dr. Agarwal has already mentioned about coin tosses, so it's the most basic probabilistic example that anyone gives when introducing randomness in events. All right. So, but first, before I go ahead into the subject of probability, I'll be talking about something more basic in mathematical analysis, which is a well-known series in mathematical analysis. So let's just go ahead and see how these things comes in. All right. So there will be three parts to my talk. So initially, I will discuss about something called this harmonic series. Then I will introduce some mathematical framework behind this very simple random experiment called coin tosses. And right at the end, I'll try to take the mix of these two and see if some interesting comments can be made. All right, so let's start. So I'll start with something called the harmonic series. All right, so this comes up in a very interesting physical experiment. So you take a string, fix it on both ends and flick it. All right, so it will start to vibrate. And once it starts to vibrate, it will have a fundamental frequency or a natural frequency, the tone you hear from the string. All right, so the fundamental frequency, I am denoting it by F1. So it's also called the first harmonic. And the next level, you get other harmonics, which are called these overtones, with frequencies which are exact numeric multiples of the natural frequency. So the second overtone you will get with 2 times the natural frequency, and then third one you will get with 3 times the natural frequency, and so on. Now, once you have understood about this frequency, let's look at the corresponding wavelengths. So what happens is that as long as the string is kept fixed, the wavelength times the frequency, that's a constant. So therefore, the corresponding the
이게 가만 왔어요.
Look at the 8th term of the partial sum sequence, then using the same idea, the first 4 terms already dominate this part here, and then the last 4 terms that you see here, you again dominate it using 1/8. So there are 4 terms here, each will be dominating 1/8, and that will contribute an extra half here. All right, so I hope the idea is now clear that look at the last term here, all the other terms marked in red are bigger than 1/8. So there are 4 terms here. So therefore this summation is at least 4/8, which is half. All right, so more generally, if you repeat this argument, you end up with this observation that if you look at the 2 power kth term of the sequence of partial sums, that is strictly bigger than 1 plus k by 2. Okay, so this is a general observation that you can simply iterate the argument that I have already mentioned, and you end up with this inequality. All right, but then something interesting happens here. So if you take this k to be very large, then 1 plus k by 2 is also very large. So for example, if you want the s2 power kth term to be bigger than, let's say, 1000, then you choose k to be, let's say, 2000, then you get 2000 by 2 plus 1, that is already greater than 1000, right? So all I am saying is that the original series that is adding up the reciprocals of the integers, the terms are getting very small, but if you add a large number of them, you get certainly a very large number, right? So, and this is what this lower bound is showing us. So you have to choose a very large k to exceed the level that you want to go after. All right. So now observe that this sequence of partial sums that you are looking at, they are of course positive. Then they are adding up all these, they are obtained by adding up these reciprocals of integers. So these terms are strictly increasing in n. And then since we have shown this lower bound, the terms in the sequence are unbounded. All right. But then we have already remarked that for the original series to converge, what we need is that sequence of partial sums should be bounded, right? So that is already violated, and hence the series that we are focusing on, the harmonic series, cannot converge, all right, because the sequence of partial sums is unbounded. So hence the sequence of the series of the harmonic series cannot converge, and it's actually divergent. So what the observation about the sequence of partial sums show is that these sums go up to infinity, right? So as long as k is chosen to be very large, this summation exceeds any level that you choose. It goes up and up. It goes to infinity. So you can say it in this way that the harmonic series diverges and diverges to plus infinity. All right, so this is a very simple fact that you see in mathematical analysis, that even though the terms 1 over n, they are very small for large enough.
I have one question.
Yes, please. Yes, please go ahead. Okay, fine. So maybe we'll answer the questions at the question answer session. All right, so I'll just go ahead. So even if the original terms 1 over n, they are very small for large enough n, the series, as soon as you add up large number of these terms, they exceed any level that you choose. So this is seen in any basic course in mathematical analysis. All right, so now we are interested in a slightly different question. So we have already seen this inequality, this lower bound for the sequence of partial sums, and let's now ask this question: how fast does this SKs grow? All right, so how large? So we already know that they are increasing and increasing to infinity, but how fast do they grow? So we already have this lower bound here for terms corresponding to 2 power k, right? So choose m to be 2 power k and then rewrite this inequality that we have proved. So s subscript n is greater than 1 plus half log to the base 2 m. So that is what I am just changing the index from k to m just by changing variables here. Alright, so this is the lower bound here. So this is true for m which is of the type 2 power k. But then just to get an idea, so we can say it in this fashion that as long as this sequence of partial sums Sm, they are strictly increasing, they have this lower bound given by some expression involving log to the base 2, right? And then of course there is a standard upper bound given by 1. So for each term 1 over n, that is strictly less than 1 for all large n, and hence by adding up all these terms that you see in the sequence of partial sums, if there are k terms, you get the standard upper bound k. Alright, so you can put all these observations that I have mentioned in the note that the order of growth of the SKs is at least logarithmic. So it exceeds this, if you plot the sequence of partial sums in terms of m, then if you also plot the log function, then the sequence of partial sums will be above the log function. So it's at least logarithmic, but then the order of growth is bounded from above by k. So it cannot grow faster than k, so it's smaller than k. All right. Now we want to actually say that this growth is exactly logarithmic. All right, so this is a very interesting fact. And to do that, what we do is that we split the idea, the proof, into two special subcases, two special steps, which we put it as subclaim 1 and subclaim 2. All right, so our idea is to show that the sequence of partial sums grow according to a logarithmic factor, right? And now instead of in the previous slide we have used log to the base 2, but just to standardize things nicely, I will start using the logarithm which is all with respect to the base e, which is also called the natural logarithm. Here I am just going to compare the sequence of partial sums against the natural logarithm and going to claim that the sequence Sn minus the natural logarithm, that is monotone decreasing, and the second subclaim will say that this sequence, the same sequence Sk minus the natural logarithm, is bounded below by 0. So we are going to prove these two claims, these two subclaims, and then go make a proper statement about the growth of Sk. So remember, our main interest is to understand the growth of Sk's. All right, so to go ahead and show that, so we are now want to show that the original sequence, that is Sk minus the natural logarithm, that is monotone decreasing. So to do that, we take help from some basic inequalities. So first we start with this very standard limit. So as k goes to infinity, 1 plus 1 over k raised to the power k, so that term goes to the number e. All right, and then look at these numbers now. Look at k plus 1 numbers. The first number is 1, and I will take the number 1 plus 1 over k times. So we have in total I have k plus 1 numbers. Now the idea is that these numbers, even though I have taken 1 plus 1 over k times, but I have taken a different number 1. So these are not all of them are equal, and hence if we apply the arithmetic mean greater or equals to geometric mean for these k plus 1 numbers, I will get an inequality, and if you do the simplification in the inequality, you will end up with such an inequality. All right, so I will take such numbers, apply the arithmetic mean greater or equals to the geometric mean, and I will end up with this inequality. What does this say? This says that the original limit that I have mentioned right at the beginning, 1 plus 1 over k to the power k, that term and the next term, so the next term corresponds to k plus 1, that term is slightly larger than, that is larger than the kth term, right? So the sequence that we have mentioned in the first line, that is strictly increasing and increases to the limit e. All right. And then you can change the powers a little bit. You can play around with the numbers and show that instead of taking 1 plus 1 over k to the k, you can now raise it to the power k plus 1 instead, in which case this sequence will turn out to be strictly decreasing, but then it will have the same limit and it will converge to that limit e. All right. So we now have two different sequences. The first sequence is 1 plus 1 over k to the power k, and the second sequence is 1 plus 1 over k raised to the power k plus 1. All right. So both converge to e. Now, taking this into account, I now have this nice inequality. These numbers increase to e, so they are strictly less than e. These numbers decrease to e, so they are strictly less than e. So I have this nice inequality here. This is true for all k. All right. Now let's take the natural logarithm on this inequality from both sides. What we end up with is that k times natural logarithm of 1 plus k, then strictly less than log of e to the base e is just 1, and then strictly less than, so this is k plus 1 times natural logarithm of 1 plus 1 over k. All right. So by understanding the limits of 1 plus 1 over k to the power k and 1 plus 1 over k to the power k plus 1, by understanding the limits and their nature of monotone decreasing and monotone increasing, we have ended up with this nice inequality, which can be reframed in this format. As we will see, this is the inequality that will help us understand the main growth of Sk. All right. So that is our target. So please remember that. So now we are focusing on log of 1 plus 1 over k, and we end up with this very nice inequality that the natural logarithm of 1 plus 1 over k is bounded from above by 1 over k and bounded from below by 1 over k plus 1. So this is a very nice inequality, and using this last inequality, we now claim that Sk, the sequence of partial sums, if you subtract out log k, that sequence is monotone decreasing. All right, so that is my claim. So how do you see this? So to see this, observe that you look at the kth term of the sequence and subtract out the k plus 1th term. So now Sk is the addition of all the reciprocals of natural numbers up to k, and Sk plus 1 is the addition of all the reciprocals up to k plus 1. So if you subtract out this part, you get minus 1 over k plus 1. And if you look at the other terms involving logarithm, so that is log of k plus 1 minus log of k. So I have just rewritten it in this form using the standard formulation, standard properties of logarithm, is that this is log of k plus 1 over k. I have just written it in terms of 1 plus 1 by k. So I hope that calculation is clear. So all I am saying is that log of k plus 1 minus log of k is log of 1 plus 1 by k. So that is a very simple observation. Now use the previous inequality. So log of 1 plus 1 by k is greater than 1 over k plus 1. So hence this term here, log of 1 plus 1 over k minus 1 over k plus 1 is positive. All right. So therefore the sequence is monotone decreasing because the term k plus 1 is smaller than the term k. All right. So that proves the first subclaim that we targeted. All right. So next we go for the second subclaim, and as we will see, this basic inequality that we have shown again will help us prove the second subclaim. All right. So the second subclaim is that the sequence Sk minus the natural logarithm is bounded below. So in the first subclaim, we have already shown that this sequence is monotone decreasing. Now we claim that this is bounded below. So to do that, again, this is the inequality we have shown in the previous page. Again, just to recall, this k plus 1 over k, I have just rewritten as 1 plus 1 over k in the previous slide. All right. So in the previous slide, we have used the left-hand side of the inequality to claim that the sequence was monotone decreasing. Now we will use the right hand side of the inequality to claim that the sequence sk minus the natural logarithm is bounded below. So how do we do that? So look at sk now. So sk again by definition is the sum of all the reciprocals up to the natural number k. Alright, so these are the terms. Now if you use the right hand side of the inequality here, first look at k equal to 1. So for k equal to 1 over 1, that is just 1. So that is greater than log 2, right? So that's exactly what I have written here. Next, for a half, you put k equal to 2 here. So half is greater than log 3 by 2, right? So repeat this argument. So each term here is strictly greater than each of the terms here. So addition will be dominated. So sk is greater than this addition of all these logarithms. And then use the basic properties of logarithm to say that this addition actually turns out into the product of the arguments here. So you just take the product of all these terms here. This product simplifies to natural logarithm of k plus 1, which is of course greater than log of k because natural logarithm is an increasing function. All right. So in which case sk is greater than log k, and hence sk minus log k is strictly positive. Therefore, it's bounded below by 0. All right. So this proves the subclaim 2. So all right. So let's take a stock of the situation. So let's just go back. So I wanted to say something about the growth of the sequence of partial sums. What we have showed is that the sequence is monotone decreasing and bounded below by 0. So these are the two things we have shown. Now I claim that these two things together will allow us to claim that the sequence of partial sums has a logarithmic growth. So let's see that. All right, so let's put things together and focus on the growth rate of the SKs. So we saw that it's strictly decreasing and bounded below by 0. So in particular, so these terms that you see here are positive, and since they are strictly decreasing, therefore it's dominated by the first term in the sequence. So you put k equal to 1 here. Natural logarithm of 1 is nothing but 0, so that will turn out to be 1. All right. So this inequality, if you just rewrite it, it just turns out by saying that sk takes value between log k and 1 plus log k. So that's a very interesting statement, and that basically says that sk is taking values between the natural logarithm of k and 1 plus natural logarithm of k. All right, so hopefully this idea is now clear that sk, we can say that sk has a logarithmic growth. All right, but now if you have studied some basic properties of convergence of sequences and all that, you will actually say that no, we have actually proved something more. So let's see that. So we have seen that the sequence sk minus log k is strictly decreasing and bounded below by 0. So again, this is a very basic fact that such sequences must be convergent. All right. So if you have a strictly decreasing sequence and which are bounded below, they must be convergent. In which case, I will now look at this limit. So let's call this limit as gamma. So this is very interesting now. So we have originally started looking at the harmonic series. We said that that is divergent. That's good. But then we focused on and that we said that okay, it has a logarithmic growth. All that is fine. But then at the end, we have proved something more. That is that sk minus log k, that sequence converges, and we call the limit as gamma. Now, this was originally observed by the mathematician Euler in 1734, quite a long back now. All right, so it's now called the Euler's constant. All right, so we will denote it by gamma throughout this talk. So we will now focus on these properties of gamma. All right. So using this convergence, we can actually get some idea about the value of the limit, which is gamma. So let's look for various values of gamma. So of course, since the convergence happens, then for any epsilon positive and for large enough k, you will say that the values sk minus log k will lie between gamma plus epsilon and gamma minus epsilon. So that is the standard definition of a limit. So for any epsilon positive and large enough k, these values will lie between these constants gamma plus epsilon and gamma minus epsilon. So you have a very small interval where all the values are concentrated. But then rewrite this inequality and say that the original sk is now taking values quite close to gamma plus log k. So this is now a very sharp estimate about the growth of sk, right? So as soon as you have observed the convergence of sk minus the log k, you have a very sharp estimate of sk's, and that sharpness can be you can choose it on your hand. You will choose that epsilon, which is the error bound, right? So sk's is taking values very close to gamma plus log k. All right. So that that information about convergence actually leads to very nice results. All right. So now let's focus on that limit value, the constant, the Euler constant. Let's look at the values of that. So what do we know so far is that the sequence that we started with is bounded from above by 1, and the sequence was also positive. So therefore, if you look at the limit of this sequence, that will take value between 0 and 1. So this is a very standard fact that if the original sequence is bounded between 0 and 1, the limit is also bounded between 0 and 1. All right, and since the sequence was strictly decreasing, it will of course not take the value 1. So that's why this is a strict inequality. All right, but then this upper bounds that you see here for the sequence, so you can instead choose other terms, like look at the term for k equals to 2. Since the sequence is strictly decreasing and converges to the gamma, so therefore these are all upper bounds of gamma, right? So look at the value corresponding to the term 2. So S2 minus log 2 is also an upper bound of gamma, and that is approximately close to 0.8. All right. So that already is quite smaller than the number 1, right? So that's already quite smaller. And if you repeat and go to the next term, S3 minus log 3, that will turn out to be something close to 0.7. So gamma is upper bounded by all these values. So if you repeat sufficiently many times, you get some very nice upper bound for gamma. All right. So that is about the upper bound. So is there any information about lower bounds? So instead of looking at the original sequence, so that was, we had looked at the sum up to 1 over k. If you chose to look at up to 1 over k plus 1, all right, this is slightly smaller, but subtract log k as before. So we are forgetting to, we are not looking at the term 1 over k here. We are just adding up the terms up to 1 over k plus 1. And of course, here we have to start looking at k greater or equals to 2. So if you again look at this sequence, you can show again using a similar argument that this sequence is strictly increasing, and this sequence will also have the same limit, which is gamma. But since this sequence is having a different behavior, meaning this sequence is strictly increasing, terms in this sequence are now lower bounds for gamma, right? So then these terms will give some lower bounds. So then look at k equals to 2 and k equals to 3 just to see some values. So k equals to 2 will give you 1 minus log 2, which is close to 0.3. And then for k equals to 3, you will get some value close to 0.4. So keep doing it, and just up to this, you can immediately say that gamma is strictly greater than 0.4. So in the previous slide, we have found an upper bound for gamma, which was 0.7. We have a lower bound for gamma, which is now 0.4. So if you repeat, you will get sharper and sharper bounds. All right, but then you can now ask, what is the exact value of gamma? All right, but this is a very interesting question. So what is the exact value? So short answer, the exact value of gamma is unknown. All right, so see, you started off with a very nice sequence, nice series, which is the harmonic series. This is taught in the basic course of mathematical analysis. We all learned that this is divergent, so we have already discussed that part here. But then the according to that argument, whatever we have discussed so far, we ended up with this gamma. Somehow we ended up with this gamma, and we still don't know the exact value as gamma, right? So see, the Euler talked about this gamma in 1734, and close to 300 years has passed already, and still we do not know exact value of gamma. So what exactly do I mean by exact value of gamma is that you write it in terms of some other known constants or some known numbers, right? So using square roots or other things, right? So yet we do not have a closed form expression for gamma. We only have lower and upper bounds for gamma, or even some approximations of gamma. So so now with computers you can do do the computation up to very large terms, and and I think up to thousands of decimal places this has been computed, and approximately it is 0.5772. All right. So but then again, the exact value of gamma is unknown, right? So if you can express it in terms of some known constant, that will actually be a new result. So this is an open problem. All right. So let's just look at another open problem, another representation for gamma. So look at the term 1 over k. This term 1 over k can be represented in terms of an integral from k to k plus 1 using the floor function. So the floor function is the greatest integer less than or equal to x. All right. So most of you may be familiar with the box function. So this is the floor function, which is the greatest integer less than or equal to x. So this is the floor function just to distinguish it from the ceiling function. So the ceiling function is the greatest integer greater than or equal to x. So this is the float function is the usual box function, by the way. All right. So I will use the float just to distinguish it from the ceiling. All right. So if you write it in this way, then the sequence of partial sums can be written as an integral from 1 to k of 1 over float function. And also recall that the logarithm of k can be written as an integral of 1 over 1 plus 1 by x, right? So this is a standard integration result that we already know. If you put these two together, sk minus log k, then you end up with this integral representation for gamma. So gamma is the limit of sk minus log k, and write the sk minus log k in terms of the integral from 1 to k. You can get this integral representation of gamma. So therefore gamma is equal to 1 to infinity 1 over floor x minus 1 over x. So that's the integral. If you look at the integrand here, that integrand is non-negative. Therefore, if you choose to do the integration from 1 to some number, so that will of course again give some lower bounds or some approximations to gamma, and that will give you the some ideas of values of gamma. So using approximation techniques for integrations, you can also get some ideas for gamma. But as I said, we still do not know the exact value of gamma. So this is an open question. In fact, there are many such open questions related to gamma. So let me just talk about a few of them. So in a mathematics lectures, it's actually customary that you mention some problems to motivate the audience. So we already have an open problem that we do not know the exact value of gamma. And then there are very nice other open questions which are not yet known. So I do not yet know whether gamma is a rational or irrational number. That means that whether I can write it as a ratio of two integers, right? So that's a rational number. Ratio of two integers will give a rational number. If it cannot be represented in that form, it's called an irrational number. And then for experts in the audience, we also do not know whether gamma is algebraic or transcendental. So I am not going to explain the terms here. This is for the experts. This is another type of numbers which we look for. And again, we do not know whether gamma is algebraic or transcendental. So these are some of the open questions that are related to this Euler's constant. All right, so let's finish up the discussion about the harmonic series here with a final slide. So we started looking at the series 1 over n, summation of 1 over n. But then let's go back and look at another familiar series. So here what we do is that we alternate the signs. So we put plus signs and minus signs alternatively, right? So alternatively. So that means the first term keeps the plus sign, then you put the negative sign and so on, right? So this is also called the alternating harmonic series. Now, of course, this series does not converge absolutely, meaning if you take the modulus of the terms and try to compute the summation, that will go back to the summation 1 over n, which we discussed very extensively. And then we also already know that that diverges. So this series does not converge absolutely. But this is also a very standard fact in mathematical analysis, that such a series which is made up of this alternating signs is convergent. So this is usually checked under this Leibniz test, or which is also known as alternating series test. So if you use that, you can actually show that this series converges, and you can actually compute the limit using a series for the natural logarithm, and this sum turns out to be natural logarithm of 2. All right. So since the series does not converge absolutely, but converges itself, so we usually say that such series is conditionally convergent, right? So just to drop the term, but we are not going to explicitly use that in the lecture. All right. So that's where I finish up the first part of the discussion. So we have already talked a lot about the harmonic series, and now we have not brought up any probability, right? So let's bring in probability. So what is a coin toss? So start with a coin and think of the sides, so one side as head, another side as tail. So that's a standard way of talking about a coin. And then if you toss the coin, then you exactly get one outcome, one of this head and a tail. But before you toss the coin, you still do not know what will turn up, right? So even before doing the tossing, what you know is that either one of head or tail will come up, but you do not know exactly what is going to come up, right? So this outcome is not known in advance. And then you can repeat this multiple times. So you can toss the coin multiple times. So this is what is actually a very simple example of what is known as a random experiment. You can repeat it multiple times. You know all possible outcomes, but you do not know for a specific trial exactly what will be the outcome. Until you do it, you do not know the outcome. So that is a very simple random experiment. Now denote the outcome of one experiment by capital X. Just to frame the problem, just to put some mathematical notation into it. So we'll look at capital X as the outcome of one of the experiments. So this is what is known as a random variable. So what you have for that specific point is that you will get a fraction p, which is some number between 0 and 1, is that you will get with that fraction of the times you will get heads, and that so 1 minus p times that fraction of times you will get tails. So that's basically the idea of a coin toss. Now if you have a fair coin that it's unbiased, it does not distinguish between head and tail, it does not put preference on head and tail, you should have p equals to half, right? So it should give you head with exactly half probability, tails with half probability. But here we are looking at a general problem that you could have a coin which is maybe favorable more towards the head or more favorable to the tail, in which case you will get this some number p between 0 and 1. All right. Now using these terms head and tails, it's hard to do some kind of computations. But then what you can look at is that you think of heads as winning and tails as losing. So if you put some numeric values to it, so think of head as +1. Okay, so winning some number, winning some amount, and then tail as losing some amount. So if you put it that way, then X, capital X, the random variable, is taking value plus and minus 1 respectively with probabilities p and minus, probability p and probability 1 minus p. So this is a very standard formulation of the probabilistic version of the coin toss. All right. So now it's a standard calculation that says the average value of the thing about the winning amount is 1 minus 2p, and the variance, which is the fluctuation about this average, that is this quantity. So this can be computed easily, so I am not going to discuss this. So these are very basic properties of random variable x. All right. But then so that was for one single toss. So suppose you keep tossing the coin, and then if you keep tossing the coin, let's denote the outcome of the nth toss by xn. So nth toss is a head and a tail with these probabilities p and 1 minus p. And then as long as you repeat the experiments, these outcomes, they are independent. So they do not affect the results of others. So then if you look at the corresponding values again in terms of numeric values as +1 and -1, you again get the same values, that the average is this and the variance is that. All right. So these are some basic ideas about repeated tossing of about coin tosses. All right. So let's now mix the things that we have learned so far. So we have a divergence of the harmonic series, and we want to mix it with coin tosses. So how do we do that? So we have already seen that the series, just by adding up the reciprocals of the integers, that series diverges. So that goes up to infinity. But if you use alternating signs, it converges, right? So then it's a very standard fact about series is that if you have a convergence of a divergence of a series, if you are given the series and if you change the first few terms, let's say first 2 terms or first 10 terms and so on, if you change that many terms but keep the other terms intact, then the convergence or divergence is not affected by that. All right, so you can ignore first few terms and look at the rest of the terms. So that will tell you about the convergence and divergence of as the original series. Here we do some modification now. So let's first look at this series. So what I am doing, so I am first fixing a positive integer n naught. So think of n naught, let's say for example n naught could be 10. So what I will do, I will change the signs of the first n naught terms, so first 10 terms, and keep the other terms intact. So if I change the signs of the first few terms, the convergence or divergence is not affected. So the same feature will be remaining. So if you modify the first n naught terms, then you have divergence here. And if you modify the signs here for the first 10 terms, it still have the property of convergence. But then let's do it more methodically. So toss a coin. If you obtain in the nth trial, if you obtain the head, you attach the plus sign. So that's where the +1 comes in. So if you obtain a head, attach the sign +1 to the nth term, and then for the tail you attach the negative sign. So just do it more this methodically. All right. So we are modifying the original series, the first few terms by coin tosses. So you change the signs. If you obtain a head from the nth trial, change the sign of the nth term by plus, just keep it as plus, otherwise keep it as minus. All right, so that's the methodology. So then if you recall that the random variables that you have put as +1 and -1 with probability p and probability 1 minus p, then you can restate that convergence or divergence in this way, that you multiply by these numbers. So you see that let's just focus on the first series. So let's forget about the other one. Let's just focus on the first series. So I am now looking at the first n naught terms. So if I multiply the terms by the random variables xn, then if I have head, I will attach a plus sign. If I have a tail, I will get a negative sign. So that's exactly the methodology I am adopting to change the signs. But what we have so far is this, that if you do it for finitely many terms, first few finitely many terms, then the original convergence or divergence is not affected. It's not changed. So if the original series diverges and you decide to change the signs this way, then it still diverges. If the original series were convergent, you change the signs this way, it still converges, right? So this is done if you do it for finitely many terms. But then let's try to think of this question. What happens if you do it infinitely many times? So what do we mean by that? So look at the original harmonic series and then do the coin tossing infinitely many times. So let's say you are allowed to do that. Then you get plus signs and minus signs mixed, right? But now we don't have a result in real analysis that helps us. So far in the real analysis, what we know is that if you change the signs for finitely many terms, then the original convergence or divergence is not affected. But what if you do change the signs for all the terms using these coin tosses? So you are adding plus signs or minus signs according to the coin toss for the nth toss, right? So if you get head, you put a plus, otherwise you put a minus. All right, so you get this addition of all these random variables now. So I will, just for simplicity, I will now call yn as 1 over xn, and then we are now asking about the convergence or divergence of this random series. All right? So we are adding up all these terms. I understand. Thank you. Thank you for the reminder. So I am just adding up these terms, and then what we have is that these are all random variables, and I am now asking about the convergence or divergence of the random series. All right. So then what you have is this. So these random variables yn has these properties. Expected value of yn is can be computed very easily. So that is exactly 1 over n times the expected value of xn that we had already mentioned. So that is 1 over n, 1 minus 2p. And then you get the variance of yn, which is 1 over n squared of the variance. So variance is scaled by the square of the scaling, right? So if yn is 1 over n of xn, so then the variance of yn gets affected by the square of the scaling. So that is 4 over n squared, this quantity. And also, as long as xn's are independent and you define yns this way, this sequence of random variables y1, y2, yn are independent. All right, so these are the basic facts about the sequence. And then we are basically asking what happens to the random series. All right, so let's just look back again. So we originally had the harmonic series, which was adding up all the reciprocals of the integers. So that is the terms 1 over n. Now we are saying we will attach signs plus 1 or minus 1, and we would like to know what happens in general. What happens to this random series now? What happens if you add up these terms? So in probability, can you make a statement that whether this will converge or whether this will diverge? All right. So to do that, we first look at the special case when the coin does not put specific bias on the head or the tail. So if you have the probability of head and the tail both to be half, in which case, so you can now state this standard calculations. So expected value of yn now turns out to be 0. So these are mean 0 random variables. Variance is exactly 1 over n squared. And as stated earlier, this sequence of random variables are independent. All right. So you have all these results. And then this is a general result due to Kolmogorov. So it's actually called Kolmogorov's 2 series theorem, but the result I am going to state is a special case of that. So the result can be found in this book by Patrick Billingsley. The name of the book is Probability and Measure. All right, so what is the result? So I'm looking at mean 0 random variables, which are independent. And if you are able to add up the variances, then the probability that this series converges is 1. All right. So in our case, when p equals to half, the variance of yn is 1 over n squared. And again, this is a very well-known series in mathematical analysis. And we show it as an example that 1 over n squared is convergent, right? So summation over the variances, which is summation of 1 over n squared, that of course converges. So in this special case, when p equals to half, you say that the original harmonic series converges with full probability. All right, so you toss the coin infinitely many times, change the signs, as long as the probability of success and probability of head and tail are the same as half, in which case you will always have that series to be convergent. All right, so this is with full probability. But then you now ask, what happens in the other case? So let's look at p not equal to half. So here what do you have? So again, the average is now is this quantity, but since p is not equal to half, the average is non-zero. Variance again, sorry, this is a typo here. This should not have been there. So variance, so forget about this 1 over n squared here. So I'll make the correction. So the variance is just 4 over n squared, p times 1 minus p. So forget about 1 over n squared here. But then the original sequence of random variables are still independent. But the main property here is p is not equal to half. All right. So here we have to apply a more general version of the theorem that we mentioned in the previous slide. So this is called the Kolmogorov three-series theorem, and it's again available in the Billingsley book. So in this special case, when p is not equal to half, so when the coin actually puts some bias towards the head or the tail, then in which case this random series that we talked about, so putting the signs in this order, so that will ensure that the series diverges. All right, so you get complete dichotomy here. So if the coin is fair, if it puts equal probability to head or tail, then the series converges. If it does not, then the series diverges. All right, so this happens with full probability. All right, so hope you have enjoyed the talk, and thank you for listening. So, and questions and comments are welcome.
Thank you, Supriyo.
Yes.
This beautiful talk, and this is really interesting because it really interconnects the analysis and probability beautifully. And there is a question, I think, in the chat box. Let me see. Okay, there's a question from Nityo Das. If I consider the case of tossing a dice, how can I decide the numerical values corresponding to 6 outcomes? Please.
All right, so I don't really understand the question. So if you toss a dice once, you get exactly one outcome. So possible outcomes are 1 through 6 by tossing a dice. But if you toss the dice once, you get exactly one outcome. But that you have to see after tossing the dice. And you just observe that in person, right? So that's the observation of the sample that you obtain from the experiment. I hope that clears up the doubt.
Okay, and if anyone has any questions, so please unmute yourself and go ahead. This is our question answer session. So, okay, there is a question from Ovinik Sukla. I have one question. In the last theorem, where series converges, can you identify the limit with some probability? Or can you say that the series converges to some random variable? And when can we identify the variable limit?
All right, so in general, the theorem that I have stated, it does not say anything about the limit. But then if you, in general, again, I'm just making some general comments. So first comment is that the Kolmogorov's two series theorem that I have referred to, it just talks about the convergence or divergence. Right? Now, next thing is that if you add up random variables, you get a random variable. So the limit is always a random variable. Right? So the convergence or divergence, whatever I am saying in probability, that basically refers to the limit random variable. So a priori, we cannot say that the limit is a fixed quantity. It's actually a random variable. And I am not aware of any specific results that allow you to actually compute the limit random variable in this specific case. So I am not aware of the result, aware of any such result. Yes. So I hope that clears up the doubt.
There's another question from Arvind Kumar that can we sum any other series in this manner?
Yes, sure. So the result that I have stated, the Kolmogorov's 2 series theorem or the 3 series theorem, I have actually, if you go back, look at the slides, maybe that will be shared later on. So if you look at the slides, the theorem that I have stated is actually pretty general. If you look at any sequence of random variables with these properties, let's say they are mean 0, they are independent, and their variance is summable. In this case, the series summation yn that will converge, all right? And then the 3 series theorem is a slightly general version of that. Just to avoid technicalities, I didn't state it. But for any sequence of random variables, as long as they are independent, and then you know something about the mean and the variances of the individual terms, you can comment about the convergence or the divergence of this random series. So again, I would request you go back and look at that book by Patrick Billingsley. So they are very standard results in probability theory. Yes.
Thank you, Supriyo. And there is no other questions. So, okay, there is a question from Dr. Shankaran P. that in slide 17, how can you change upper limit to infinity from k?
All right, so maybe I will share the screen again and then look at that slide. Okay, so let's go back to slide number 17. All right, so here what I am saying is that, so here I am looking at the limit of this terms which I already know to exist. All right, so I already know that this limit on the left hand side exists. I am just rewriting the terms inside, which is sk minus the natural logarithm. Now sk minus natural logarithm I have written in terms of integration from 1 to k, but then again I already know that this limit exists. So hence this integration has a limit which we usually denote by 1 to infinity of the same limit. All right, so I hope that clears up the doubt.
And there is another question from the YouTube stream that random series is always convergent or not. This has been asked by Ranjana Kumari Srivastav.
No, in fact, if you have followed the talk, in the special case, in the case when the coin is biased towards the head or the tail, so p is not equal to half. In that case, we have actually shown that the series diverges, right, with full probability. So in general, you have to look at all these criteria and then make your comment. So again, I would request the audience that please take a look at the book by Billingsley. So there these results by Kolmogorov are stated, and the most general result is called the Kolmogorov's 3 series theorem, and it actually gives you a necessary and sufficient condition for this convergence or divergence with full probability.
Yeah. Okay, thank you, Supriyo. I think there is no other questions.
So. All right, so I'd like to thank the audience for the attention, and I would like to apologize to the next speaker as well as the audience that unfortunately I have another meeting to attend, and I have to leave. So I apologize to the next speaker as well as the audience. So again, I enjoyed the discussion here and hope you have also enjoyed the same thing. All right, thank you.
Okay. Thank you, Supriyo. And we will meet again soon. Yeah. So now I am inviting our senior professor of our mathematics department, Dr. Kanailal Dotto, to introduce our next speaker, Somir Kaur, over us. Okay. So I'm giving.
Hello, good evening, everybody. It's my privilege to introduce Professor Somir Kaur. Dr. Somir Kaur has completed his degree in the year 2012 from Bankura Sammilani College and completed MSc degree from IIT Guwahati in the year 2014. He has completed his PhD degree from IIT Chennai in the year 2019. He has worked as a postdoctoral fellow at IIT Chennai. At present, he has been working as visiting assistant professor at IIT Jammu. His research area is on functional analysis and geometry of Banach space. He has several publications on SCI and Scopus Index Journal. Now he will deliver his lecture on discontinuities of monotone function. I am sure that the participants will be interested to acquire much knowledge in the subject by attending his lecture. Now I request Dr. Kaur to deliver his lecture. Professor Kaur, please continue. শুনতে পাচ্ছি না যে শুনতে পাচ্ছি না কেন সাউন্ডটা চালু করে
Hello, now am I audible?
Yes.
Yeah. So thank you, sir, for your nice introduction. First of all, I want to thank this organizing committee for providing me this opportunity to deliver a lecture in this one-day national webinar on mathematical analysis and probability. So, and we know this JK College means one of the most reputed college in West Bengal as well as in India. So I am very happy to deliver a lecture in this platform. So, okay, without any further delay, so let's start. So my screen is visible to everyone? Hello? Yes, no problem. Yes. Okay, so in this lecture, I mainly focus on discontinuities properties of monotone function. So first I will discuss what is monotone function, then it's some continuity property of this function. So what is monotone function? So consider f be a real valued function on an interval I of r. The function f is said to be monotonically increasing on I if for xy in this interval and with x strictly less than y imply f of x less than equals to f of y. So this is also called non-decreasing function, and it is also called order preserving map, like that in literature and other book is considered many ways, means by many name actually. So and similar fashion we can define this monotonically decreasing function. So for xy in this interval with x strictly less than y implies f of x greater than equals to f of y. Yeah, so this is the definition. So for example, so we can consider x square with 0 to infinity. It is monotonically increasing function. And if we consider x, that is also monotonically increasing function. Like that, if f is monotonically increasing function on some interval, then minus x is monotonically decreasing. So like that we can generate many examples. So we are considering some certain class of function. So one can expect that it will have some special properties which are not satisfied by an arbitrary function. Like Lipschitz function, we know that it is uniformly continuous and kind of thing. So okay. So we'll see that some properties of this monotonically increasing function. So okay, I'm considering f is a monotonically increasing function on this domain open A and open B, a real valued function. Now if we consider any point C from this domain, then we can talk about this left hand limit, that is limit x tends to C minus f of x, which is equals to supremum of f of t, where t is lies in open A and C. So, and similar fashion, we can get right hand limit. Instead of supremum, we will get infimum of f of t, such that t belongs to open C and open B, means open interval C and B. So, and one can just quick review what is the left hand limit. So left hand limit we denoted by a limit of x tends to C minus f of x. If it is L, so then we can get f of x minus L less than arbitrary. For arbitrary epsilon, we can get a there exists a delta such that C minus x less than delta. So we exclude that point x equals to C, such that all those x which satisfy this condition will also satisfy this condition. For a given positive epsilon, we can get a positive delta such that when x satisfy this condition, will also satisfy this condition. So then we call this this left hand limit of this function at C is nothing but L. So that is the definition of left hand limit of a function. So similar fashion we can define right hand limit, and it is easy to show that for monotonically increasing function we can get this left hand limit equals to supremum of these things and right hand limit equals to infimum of these things. And in case of monotonically decreasing function, we'll write this instead of supremum it will be infimum, and instead of infimum it will be supremum. So this that means this supremum and infimum exist, so that's why this right hand limit and left hand limit at a point it exists. So and it is easy to see that f of C minus, that means left hand limit, less than equals to f of C less than equals to f of C plus, that is right hand limit. And whenever if we take xy in this domain with x strictly less than y, then we can get this right hand limit at x less than equals to left hand limit at y. So this inequality easily means one can easily prove or easily get actually with just epsilon delta definition. If someone use this epsilon delta definition, so easy to derive this thing. So I am not spending much time on this. Okay, so that means if some function is continuous at C, then it should satisfy this condition. Means left hand limit and right hand limit should be equals to f of C. That is C is the point from this domain. And now in case of monotone function, it can happen that monotone increasing function that it is f of C, or many possibilities will come, or like it can be happen that so, and it also can happen this type of things at the point C. So every case it is means this function is not continuous, so it is called jump discontinuity. So okay, so there are other type of discontinuity, so I am not talking about that in this lecture. So that means this function f have only jump discontinuity because of this f of left hand limit and right hand limit is exist, and it may be the case that it is not equals to f of C. So that case it is jump discontinuity. It will have jump discontinuity at that point. So okay. So similarly, we can get a similar result for monotonically decreasing function also. So now consider this theorem. If closed interval AB to closed interval CD is monotone and onto, then F is continuous. So how can we get this result? So okay, intuitively, if we see, suppose if we consider this AB closed interval and CD. Now suppose f is not continuous, means we are proving by contradiction. Suppose f is not continuous at a point E. Okay, then what will happen? It will happen that at the that means it will happen that f of C minus does not equals to. So okay, I am considering it is monotonically increasing. Okay, so and similarly we can consider monotonically decreasing things also. So that case it's f of means left hand limit at E does not equals to right hand limit of that function. So this for monotonically increasing things we can get this inequality. If it is if discontinuity arise at the point E, so we will get this thing. So that means this function will not cover this value. So if we consider this closed interval and if we subtract this point, so this function will not take this value, whereas we can easily get that these things fully contained in this interval, means in this codomain, correct? So we can, so it will violate this onto condition. So that means this function is continuous. So now using this theorem, so what can we get actually? So using this theorem, we can get this Cantor function, which is defined closed interval 0, 1 to 0 is continuous. So to know this Cantor function, we have to we have to get this what is Cantor set. So okay, I just quick recall what is Cantor set. If we consider this closed interval 0, 1, that means in line it is something. On x-axis it is like that. So and C1 is, sorry, so that means we are removing this open interval 1/3 to 2/3 from this C0. So that means we can get this is this part. So now I am considering C1 equals to this one. So this is 0, this is 1/3, this is 2/3, and this is 1. And similar fashion C2 will consider, we'll make this part into three part, then we'll remove that open interval, middle part, means open sense, and these things also will remove that open part actually. So it will something like, if it is 0, then it will be something 2/9, and sorry, this will be 1/9, this will be 2/9, and this will be 3/9, that is 1/3. So we'll remove in this case 2/9 and 1/9 and 2/9, and in this case also we'll remove this, it will come 6/9. So it will remove 7/9 and 8/9 in second step. So ultimate will get this C2, and by this way, in similar fashion we will consider C3 like that. So ultimate we will get a sequence of sets. Then if we consider this intersection of all those sets, so okay, so observe that all those sets are closed sets. Okay, so that means intersections of a arbitrary closed set is closed. So again we will get this is C is closed set. So, and using nested interval theorem we can get this C is non-empty also. So that means we will get this intersection is non-empty, and we will denote it by C, and this is non-empty and closed. So okay, so we call this set is Cantor set. So this one can observe if X belongs to C, that means this Cantor set, so that X can be written as 0.2 and similar fashion in base 3. Means if we write ternary representation of the point Ax, then we will get these things where Ai is belongs to where Ai will be either 0 or 2. So it may be the case when if we consider like 1/3 in ternary representation, it will give this 0.01, means in base 3. So that means this is also belongs to this Cantor set, but it does not look like in this form, because Ai is of the form 0 and 2, but whereas this A1 is 1. So there are another representation for this point. So we can write this point is 0, 2, 2, 2, and if we what is this value? These things can be written as 2y3 square plus 2y3q plus 2y34, this series, and these things can be written as 1/3 plus, we can assume this other part are all 0, means A2 A3 dot dot. So that means it will come like this way. So we can see that this will give 1/3 and this will give also 1/3. So that means this point has two representation. So that is 0, 1, and another is 0.0222, and it is in base 3. Like we know this binary representation, so it is also ternary representation. This is called ternary representation. So so just these things if we write, so in ternary representation it is something like this, Ai whole to the power 3 to the power I, where I 1 to infinity. So in base 3 form, so this point means if we represent a point this way, so that will be nothing but this one. Okay, so that is the things. So okay. So that means every point in Cantor set we can be written as this ternary representation where each ei is of the form 0 and 2. So now we can define a function from this Cantor set to closed 0 1 by this fashion: f of a1 a2 dot dot in base 3. That means ternary representation. So it can be written as 0.u1 by 2 a2 by 2, means I am writing rough way. So that's, sorry, a3 by 2, like that. So it is very much possible because a1 a2 a3 are either 0 or 2. So that's why we can divide this by 2. So we can get either 0 or 1, means this value we can either get 0 or either get 1. So this will consider in base 2. Okay, so that means in binary representation. So this can be this is the point in closed 0 1. So and any point in closed 0 1 can be represent as a binary, can be written as a binary representation. So from there we can get a pre-image of that point by this way. So that means this, if we consider this function f of means fc to close 0 1, it is exactly on 2, because if we consider any point in this codomain, so it has binary representation. So from that binary representation we can get a pre-image, so in C. So that means it is of the form 0.e1 a2 dot dot this kind of things, and where ai belongs to means ai are either 0 or 2. So that means so now we are getting this function, we are defining a function from Cantor set to 0 1, which is on 2. So what can we say about this means set C? Means it is countable, uncountable kind of things. Means I want some response from student side. So anyone can means suppose this is I am defining a means I construct a function f from a Cantor set C to this closed interval 0 1, which is on 2. So can we say about the C, means it is countable, or means say something about C, about cardinality of C? It is countable, uncountable. So okay, so if it is if it is onto map, and this is uh, as we know, this is uncountable set closed 0 1. So that means this will also insist us that C to be uncountable. Okay. So now in measure theoretic sense, we can get this measure of this set is nothing but 0. So that's why this Cantor set is very famous. Means in some set it is very small, that is measure of C is 0, and in some sense it is a very big set because this is uncountable set. So that's why this Cantor set is very interesting in analysis. Means this example is, means Cantor set example is very famous in analysis. So every book you can find out this example. So I'm not talking about much about Cantor set. So now we define this function Cantor set to 0 1. Now if we extend this function from whole 0 1 to 0 1, so it will give by this fashion f of x equals to defined by supremum f of y such that y is in C and y less than equals to x. So we can define this, means we can extend this function f on whole 0 1, means close interval 0 1, and we can observe that this function is nothing but means this function is onto and as well as it is monotone. And if we see the graph of this function, so it is something like this. So whatever part we remove in counter sets, like this open 1/3 to 2/3, so it will give constant value, and this part also we remove this 7 9 by 8 9. So in this part it will give constant value like this fashion. So we can this is called Cantor function. Now things is that, as I said, this is this function is onto, and we can prove this is monotone. So then by this theorem we can directly conclude this Cantor function is continuous. Correct? Okay. Okay, so I'm going to next result. I'm going to okay. So this theorem, many of us very much familiar with this result. If f is a monotone function on open AB to R, and f has a means f at most has countably many discontinuities point in AB. So how can we get this result? So let us assume that f is from open AB to R, which is monotonically increasing. So similar result we can prove for monotonically decreasing also. So in this proof, I am considering only monotonically increasing. So in similar fashion, we can prove for monotonically decreasing also. Now consider if C belongs to in this domain of this function. So we can have these things: f of c minus less than equals to f of c less than equals to f of c plus. Correct. So as we discussed in earlier slides. So now observe, if f is discontinuous at a point c, if and only if this f of c strictly less than f of c plus. That means f of, if it is not continuous, that means these two right hand side and means left hand side limit and right hand side limit exist. If it is discontinuous, so that that can be means that will say that these two value are not equal. So for monotonically increasing case, we can get this strict inequality, f of c minus strictly less than f of c plus. Now, if C and D are two different points of discontinuities for f, then this interval, this f of c minus comma f of c plus, this open interval and this open interval will be disjoint. Okay, so why this is so? Suppose means without loss of generality, we are considering C strictly less than D. So in this case, we can get f of c plus less than equals to f of d minus. Correct? So these things tell us that these two open interval are disjoint. Okay. So like that, so whatever discontinuity point will arise, so corresponding we can get an open interval, and that all those open interval are disjoint and means non-trivial open interval, means it is something like a b, where a strictly less than b kind of things. So yeah, so now tell me, if we consider this this is the collection of non-empty disjoint open interval in R. So this much we are getting actually. So what can we say about this collection? Means cardinality of this collection. It is collection of open interval. So anyone can respond. I mean, I am asking these things to student. So, if suppose we have means collection of non-empty disjoint open interval in R, so what can we say about this? What is the means cardinality of this collection? Is it countable? Is it uncountable, or is it finite? Kind of things.
Sir, countable.
Yeah, correct. So it can be means countably, means it can be finite or it can be countably infinite. So because so we can get this every open interval, we can get a rational number. So if we assign this for this open interval, if we define that rational number C and this rational number D. So this is possible because of axiom of choice. Means if we take non-empty collection, means collection of non-empty sets, then we can pick up one element from each set. Then we can define, means we can get another collection of means another set. So okay. So that means we can get this collection is countable. So these things is telling us that this function means this monotone function has countably many discontinuities. Correct. Mean each discontinuity point we can assign a open interval, and this as this collection is countable, so that means that collection of this discontinuity point will also be a countable. Okay, so this is a straightforward result. Okay, so that means it is roughly like this. If we consider some monotone function, if it is something like this, it can be point C, it can be open interval kind of thing. So we can get some open interval. Okay. Okay, so these things will not arise. So that means this will for each discontinuity point, we'll get this side open interval. For this discontinuity point, we are getting open interval kind of thing. So this all are disjoint open interval. So that's why it's means countably many. So now converse. So what can we say about converse? Suppose if we have means countable sets, if D be a countable sets in R, so it can be in open interval AB. So that can be possible actually to extend this result for open interval also. So I am talking about here from F R to R. So if suppose D is given countable sets, so then we can construct a monotone increasing function F R to R such that D is the set of discontinuities point of F. Correct. So it is not necessarily that we can only have this monotony increasing function. We can have monotonically decreasing function, because whatever F we are constructing, so that minus F will be the monotonically decreasing function. So that part is I'm leaving. So okay, so just a brief sketch of the proof. So suppose if I considering this countable set, so that means this set can be written as means we can enumerate the element of D. So that means it can be written as x1, x2, dot dot this way. So now if we consider this epsilon n be a sequence of positive numbers with this sum is finite. So as a particular case, we can consider epsilon n is 2 power n. Okay, you can consider n greater than equals to 1. So that's why this sum is finite. So essentially this sum is exactly 1 will come. So okay, so this things is very much possible. So epsilon be a sequence of positive number with this with summable actually. So now we are defining a function from R to R. Okay, you consider so by this fashion. So f of x defined by summation xn less than equals to x and epsilon n. So I am just explaining what it means. So I am taking sum over all those n in n which satisfy xn less than equals to x. So we are fixing a x in R. Now we are considering this set. All those n belongs to, so already this x1 x2 dot dot xn all are fixed and x is fixed. Now I am considering this set n belongs to n such that xn less than equals to x. So so it can be possible that this set is empty, correct? So in this case this sum will take suppose for some x, if this set is empty, this set is empty. So in this case, we will consider f of x equals to 0. And if it is non-empty, so for all those n in n which satisfy this condition, so corresponding means all those for all those n, we will consider this sum actually. So now this sum is clear to everyone. Means what I am taking. So these things is better to write all those n in n such that xn less than equals to x. Okay, so now I am claiming that this function f is monotonically increasing and it has discontinuity point at every point means at every point in D. And in other means if some points not in D, so that point this function will be continuous. So that is my claim. So first I will check this function is monotonically increasing. So for that case we are considering x strictly less than y. So now I am considering f of y equals to all those n such that xn less than equals to y, and for those n I am considering this sum. So that means then we are breaking this summation into two parts. How it is possible? Suppose this is x and this is y. So I am breaking this sum in this fashion. Okay. So that means in this part is saying all those n such that xn less than equals to x union all those n in n capital N such that x strictly less than xn strictly less than equals to less than equals to y. So if we take these two union of this set, so it will say that all those n belongs to n such that xn less than equals to x. Oh, sorry, this will be y. So all those n in n such that xn less than equals to y is nothing but union of these two sets. So that's why we are separating these two sum. This is first summation, it is coming from here, and this is another summation, it is coming from this set. So now this things is nothing but f of x, and this things is nothing but I am keeping as it is. Okay, so that means since each epsilon n is positive, so that's why we are getting this is greater than equals to 0, because in some case these sets may be empty, means all those n's which satisfy these conditions can that set may be empty, so that case it's maybe 0. So in other case it's maybe strictly greater than 0. So that means ultimate we can get this f of x less than equals to f of y. Correct. So we are getting this part. Now we'll check case by case when this for case by case means first I will consider x equals to xk for some k, and y equals to xk plus h, where h is positive number. Okay, so then we are considering same things, whatever way we are considering. Instead of y, we are considering xk plus h, and instead of y, instead of x, we are considering xk. Instead of y, we are considering xk plus h. So now, in same way, we will get these things. Now we will observe that this part is tends to 0. That means it is something function of h. So this is tends to 0 whenever h tends to 0 plus. Correct. So how is it means how it is so actually. So these things is exactly 0. So this expression is clear to everyone. I hope so. Okay, so I am considering this sum, and I am considering this limit h tends to 0. Then what will be this right hand limit of this function? So okay, so see this. If we see something, suppose this xk is appear here, and xk plus h is something like this. Now we will push this x plus h from left to right, means in this side, by making h small and small, such that this in these sets. Okay, so before that, okay, let me fix these things. For epsilon positive, since this series is convergent, so that means for epsilon positive, we can get there exists n such that n n plus 1 to infinity. These things we can make strictly less than epsilon. So this is very much possible because of this epsilon n series is convergent. So that means this tail tends to 0. So from there we can get this thing. So now make now as I am telling, so we will consider this h tends to 0 plus. That means we will push this things from left to right such a way that this 1 2 okay, so y does not belongs to in this set xk strictly less than xn less than equals to xk plus h, sorry, n. So is it for means for any I, if we take I from 1 to dot capital N, so we can make h means we can make h as small such a way that this all those 1 to dot this capital N does not belongs to in this set. So this is very much possible. So now this set is, since this 1 to dot capital N does not belongs to in this set, so this set is okay. So for that case, we can get xk xn less than equals to xk plus h epsilon n less than equals to summation n equals to n plus 1 to infinity epsilon n. Correct. So this is very much possible because I am considering 1 to dot capital N does not belongs to in this set. So that's why if we take this sum, so this sum is dominated by this sum, because this it may be the case. So it will not appear this in this case. It will not appear in plus 2 or these things. But anyway, these things is totally dominated by this value, and these things we can make less than epsilon. Correct. So that's why this when we making this xk plus h, such way that this it's means it is going towards xk from right. So that means these things is nothing but 0, because we are making as small as possible this sum. We are making this sum as much as small as possible, and that is epsilon, by making h by taking h is arbitrarily small. So okay, so that's why this limit is nothing but 0. Correct. So if it is 0, this limit, so now we can take limit h tends to 0 plus from left and right. So it will give this f of xk plus 1 right hand limit, and this will give this xk, and this will give 0. So that means we can get these things. So this is saying that f is right continuous at the point xk. Correct. So now we'll see in that f is not left continuous at the point xk. So how it's so actually. So now we'll take instead of x we are considering xk minus h, and instead of y we are considering xk. Now we are taking h positive, then we considering these things. So it is already calculated, means this f of xk is can be written as f of xk minus h plus this sum. Correct. So now so here one thing observe, this if we consider these sets, all those n in n, such that xk minus h strictly less than xn less than equals to xk, this k is always there in this set. Correct. So if we consider all those n such that xk minus h strictly less than xn less than equals to xk, whatever positive h you choose, this xk by guarantee it is there. Means sorry, not xk, this k means this integer always there. So that means this sum is means this sum is always greater than equals to xk. So now I am telling when h tends to 0 plus, that it will give exactly xk. So in similar fashion we can say that if we again consider xk minus h and xk, and if we make this h small and small, then it is going toward xk, such a way that this finite means we can such a way that this interval, this open interval, because this is open interval type, so this open interval will left out this point, means this index 1 2 dot dot capital N, means all those n which satisfy these conditions. So in those n, this set will not appear actually. Correct. So so this is very much possible whenever we make this h making h small and small. If it is
But
if it is
just interactive 1 second. Your PPT is not visible. Please share again.
oh, is it so?
No. Someone in between, someone start presenting. That's why it's gone.
Okay.
Just 1 second, he will be rejoining soon.
Hello, can you hear me?
Yes, no problem.
Okay. Sorry for this delay things because my tab is not working at this moment. So now I'm using this laptop, so I can't edit and all those things. Yeah. So now is it visible? The screen? Hello?
Okay, make it full screen. Control L.
In here it will not come actually.
Okay, then continue.
Okay.
Continue, no problem.
So what we are discussing this now we can make this f of xk plus h is f of xk plus this sum, and this sum is tends to 0 whenever h tends to 0 plus, means it is from positive side it is going towards 0 from right. So okay, so that means ultimate we will get this f of xk plus equals to f of xk. Now okay, so another case we will consider f of xk minus 1. That means left hand limit at the point xk will be the xk minus epsilon k. So for that we have to consider these things. F of xk equals to f of xk minus h and to plus this sum. So that means this sum we can get again this same logic we can means by guarantee it is this xk, means when n equals to k it is satisfied. So that's why this sum is not means going towards 0. So it is always epsilon k is there. So and other things we can make epsilon k plus epsilon by making each arbitrarily small. So in this case we can get this f of xk. Okay, if we consider this, if we consider f of means if we take limit h tends to 0 plus from left and right, so then we can get this f of xk equals to f of xk minus 1 plus epsilon k. So these things leads to this one, f of xk plus 1 minus f of xk minus 1 equals to epsilon k. So that means this function has jump at the point xk with jump with this positive value epsilon k. So that's why this f is discontinuous at every point of d. So this k is arbitrary. So we are considering xk from d actually. So k can be 1 2 dot dot means from natural number. So okay. So that means now we have to prove this f is continuous at the point x. So for that reason, for that case, that means x is not of the form xk for some k in positive integer. So for that case, we can again take x strictly less than y. So where y is nothing but x plus h, then we can consider f of x plus h equals to f of x plus this sum. So now again if we take h tends to 0 plus, so we can make this sum is arbitrarily small by making h arbitrarily small, by making h small. So that means we can get this f of x plus equals to nothing but f of x. And similarly we can take f of x equals to f of x minus h plus this sum. So these things will lead to f of, means by same logic we can get this f of x minus equals to f of x. So that means these two value are same, and it is that means these things is saying that f is continuous at the point x. Correct. So that's why we can construct this monotonically increasing function. So now if we take minus of this function, we can get monotonically decreasing function, and it will have this discontinuity at every point of d and continuous every point other than d. So this is the construction. So now in one can check if we consider this d equals to natural number and epsilon n, that means this this sequence, if we consider 1 by n type, then it is something like a step function we can get if we construct this function this way, f of x defined by this way. So we can get something a step function. So so yeah, so this all those things is very much given, means in details it is there in NL Carothar's book, which is means a real analysis book for graduate student or undergraduate student. So one can check all those results, means one can get all those things at a time actually in this book. So this is the thing. So thank you for your attention.
Okay. Thank you, Professor Somit Kaur, for your beautiful talk. And now the question and answer session will start for this very session. So if you have any questions or queries, then you can go ahead and unmute yourself and ask the presenter. So. I haven't seen any question in the chat box, and some Arujyoti Daripa is asking the name of the book.
Yeah, as I said, this NL Carothar's that is real analysis, means title of the book. And okay, if it is staff, then okay, I can write it in chat box.
Yeah, you can write this in the chat box.
Yeah.
Exactly.
Let me check actually. My screen is visible?
Yeah, your screen is visible.
So that's why this.
So any other question? So I'll write in chat box. So that is.
There's a question in the Facebook, YouTube live chat that Beth Focus Dubey has asked that please define the Cantor function, where we use it specifically, what is its mathematical significance, can it be exponential or power function?
Can it be exponential or
power function?
So exponential, it is means I didn't get the question properly.
Yeah. Actually, the question is not well posed, I think.
Yeah. Exponential means it is something it is going towards infinity when but we are taking this is restricted domain 0, 1 to 0, 1. So where exponential function is defined on whole R actually. So
yeah. And no questions is I haven't get any question in the chat box, but I have a question actually. That can we generalize this result in a general metric space?
So first problem will come, this order things we have to define because monotone function we are considering, so that means some kind of order preserving. So that means we have to define this order things on the matrix space, and here we have nice things, means right hand limit, left hand limit. So there we can't talk about this right hand limit and left hand limit. So that will be the another problem. So like that. So we can't get this nice ground actually here. This in real line we have something.
The real line is complete ordered field, so these things are very nicely suited in real line. But I'm querying about that. Can it be generalized on a matrix space, or rather more on a Riemannian manifold, where you have a Riemannian metric, and then the ordering, if you choose the proper orientation. So I think this could be a good problem if you.
Maybe some means author maybe consider these things, but I haven't seen that things actually. But many problem will come, so that things we have to address actually properly. Otherwise, we will lose this ground actually. That nice ground means.
Okay, so there's no more questions, I think. Some Gala Venkat Swami has asked that why epsilon used? Why epsilon is used?
Epsilon?
I think in the proof.
Okay. To understand that when this h tends to 0 plus, then we can make it is tends to means that function value is 0. So to get interpretation of that, we have to take epsilon positives, and then we have to check actually like that.
Okay, so I am thanking you, Professor Samir Kaur, for this nice presentation, and the final valedictory season or vote of thanks will be given by our departmental colleague, our very own Gopal Datto, and he is our assistant professor of Department of Mathematics, and he will be giving the valedictory season. Oh, I think there is another question actually in the chat box. This has been asked by Agni B Chetri, that cannot be used other than Cantor function here. Any restrictions there?
Cannot be used. No, means, can you repeat the question, sir?
I think there is some typo in the question, but the question says that can we use other than Cantor function here?
No, in the proof I haven't used Cantor function. So I just give some example actually, means where this theorem is used and this monotone and onto.
I think he hasn't followed the proof actually. So he's asking this. So okay, so Dr. Somikor, please, I'm asking you, please pin your.
Oh, stop presenting things. Okay.
Yeah. Because your face is not visible. It's fine. Okay, so there's another question from Dala Venkat Swami that why function is defined such a typical manner?
Because this set can be typical actually. This countable set it is not given actually, means nice set. So set can be typical also. So that's why function can be typical. So if we consider some, like countable set natural number. So we can define this monotone increasing function where this discontinuity arises on this natural number. So, but this given this countable set may be typical, so that's why this function will come this typical way actually. So,
yes.
Actually, we don't know that. We don't know that D actually. So it can be rational. It can be other than means algebraic number kind of thing. So.
Okay, so there is no more questions, and so I'll move on to the final part of our event. So I'll request Dr. Gopal Datto to please present his valedictory speech.
Yes. Am I audible?
Yeah, you are audible.
Thank you, Devoda. Respected all, it is my privilege to have been asked to offer a vote of thanks on this webinar. On behalf of Department of Mathematics, Jkc College, and as a convener, I am very heartily gratitude to the speakers, Dr. Supriyo Bhor, IIT Kanpur, and Dr. Samir Kaur, IIT Jammu, for accepting our invitation and sharing their graceful words. I also wish to express my gratitude to our principal sir, Dr. Santanu Chattopadhyay, and our IKC coordinator, Ashok Kumar Agarwal, for their encouragement and support. I extend my big thanks to our HOD, Dr. Ganesh Chandra Gorai, and all my colleagues who have worked from last 1 month for making this event successful. I also like to thank technical staff of Department of Computer Science, Jkc College, for their technical support. At last but not least, I thank all the participants for their active participation. On behalf of our department, I declare here the end of our program today. Thank you all.
Thank you, Gopal, for this wonderful concluding speech. And so let's finish this program here. And many thank you to all the participants. Gopal,
Hello.
okay, so I think your speech is complete, na?
Yes. No
Okay,
problem.
okay, thank you. So let me close this session and thank you all. We'll try to organize another webinar on some other topics. So I think you all will cooperate with us, and thank you for everything. So okay.
You will receive your feedback in your mail.
Yeah. I have write it down in the chat box that you will receive your feedback link through the email ID you have provided, and please fill that up properly, and so that we can smoothly generate your e-certificates. And thank you everyone for the session. So once again, I'm thanking Dr. Somit Kaur
Thank
for
you, sir.
such a beautiful lecture. So let us close this event. Thank you.